Okay, so I put a video out there on some of the preliminaries of statistics, gathering data and types of samples and stuff like that. So hopefully you either had time to watch it or you'll get time to watch it here in the next week. Basically what it just talks about is the importance of taking a good sample and getting good information, because bad statistics starts with gathering the information poorly. And so much of the statistics you see actually have that issue. Most of your issue polls, your presidential election surveys or whatever, are really poorly operated. The type of sample they take or the way they select the people that are in their samples, really very poorly done. In the medical fields, a lot of the statistics, there are statistics on the quality control side of it. I mean, the customer service desk and stuff like that, they have dropped calls or unanswered calls and time to answer calls and stuff like that. The billing side has statistics on average time to pay a bill, average size of an outstanding account, and things like that are taken. But really the important side of statistics in medicine is in the advancement of medicine, like drug testing and stuff like that. So taking a proper sample and being very careful how you handle things in that sample is really important. We're going to assume, starting out, that we have done all those preliminary things and we have taken good samples. In medical statistics, drug testing or whatever, we usually do have two groups. We have the test group, or sometimes called the treatment group, and we have a control group. The test group or treatment group is usually a new medication. The control group can either be a current medication or no medication. If it's something that we currently don't have a treatment for and we're trying to test a new potential treatment, obviously it would be a new treatment against no treatment. If we had a treatment for it, but we were hoping to find a more effective one, it would be the new treatment against the current treatment. Now, I'm just going to take the angle of drug testing here, just because it's the easiest one to refer to. And we're going to look at testing a medication against no treatment at all, no medication at all. Now, they divide up those patients based on demographics, and when you're talking about drug treatment, it's very complex. They try to match up patients by having an equal number in certain age ranges in each sample. So if you have all people that are in their 70s in one sample and in their 30s in another, well, statistically, chances are the younger group is going to be stronger and more likely to recover than the older group. Less likely to have other complications that interfere with the treatments. So they're going to divide them up by age, demographically, the same number of older people in each group. Divide them up by severity. If it's a cancer treatment, divide them up by what stage they're in, or keep them all in a specific stage at a certain level of severity. It's considerations to take. You can't have everybody in one group in stage 3 and everybody in the other group stage 1 and get a fair comparison. And then other things that would affect their recovery: strength, size and weight, health factors, something called confounding factors. If you ever read a medical study, at the end of the study there will be several pages. I don't suggest you go read a medical study, by the way, because they're like 200 pages of really dry reading material. But the very end of it will be dozens of pages of exclusions. And these are people that were part of the test, but were not included in the final result. Can you think of any reason why you would ever do that? Why you would start a test with people in this group and then throw them out of the group partway along? They die, okay? But what if it's the disease that kills them? On what condition would you throw them out for dying, I guess? Okay. Well, and if they do die from the condition that you're trying to treat them for, then they may still be included in the sample. But let's say they die in a car accident on their way here to get their weekly treatment. Well, obviously that has nothing to do with the medication. So they're not going to be included in the final results. They're not going to be the statistics. Confounding comes when you cannot separate your causes or your results. Let's say one of those people dies of a heart attack. Is that a condition that was totally unrelated? Or maybe is that a potential side effect of the medication that it causes a higher risk of heart attack, heart failure? So many medications now we're finding 10 or 15 years after they started use have cause heart conditions or kidney, liver problems. The Celebrex one that I'm sure you've probably heard about was one that I have friends that worked in medical research. It was prescribed to me for arthritis several years ago, and one of my friends found out about it and said, don't take that. We're in the process of a study right now, and the early results are saying, no, you don't want to touch it. But it took 3 or 4 years. It was 3 or 4 years later before the announcement came out saying this can be linked with congestive heart failure. So, I mean, is that medication, did the medication increase that probability, or did it cause that condition? So that's confounding. A lot of times they'll remove them from the sample just to be safe. Now I'm going to go over some of the deeper concepts on just a theoretical basis here quick, and then we'll dive into the calculations of statistics. But statistics is based on a curve, a bell curve, or distribution curve. Now, I shouldn't say that all of it is a bell curve, but most things in nature go off of this bell curve. It's called a normal curve. And things like height of people, weight of people, lifespan and stuff like that, if you were to actually plot them out, you would get a distribution something like this. The way it kind of works is this. Let's say you take a number line and put in all the possible values. Let's say that on the last test, we have scores from 60 trim it a little bit, up to 100. And I'm taking all the students I've had through the years, I'm going to plot their scores on here. So let's say we have an 84, 96, 72, 79, 82, another 84. We just keep plotting their scores on here. And you can see if I repeat one, I just put another dot up above it. And as I plot those scores, what happens is it kind of makes a shape. And if I keep plotting those points, if I draw a curve through the top point on each column, I should get something really close to that bell curve. So what this bell curve is saying, this normal curve is saying, is there's a number line down here. Let's just say it's 60 to 100 again. The height of this curve represents the number of students that have that score. So the higher the curve is at that point, the more students had that particular score. So it's really low here at 100 because very few students scored 100. Really low at 60 because very few students scored a 60. And that's what that curve means. Now when we start talking about probabilities, we can figure out how likely something is to occur by using the area under this curve. If I want to know the probability of a randomly selected student having a score between 70 and 80, well, that's just this area under that curve will help me calculate that probability. It's that area divided by the total area gives me that probability. What we normally do is we adjust the curve so its total area is 1. So then we just have to calculate that area. So statistics and medical studies and any sort of, they call it hypothesis testing, which is the formal word for it. We're not going to get far enough to get into hypothesis testing, but it's based on really unlikely events. So what we do is we make assumptions. So we make assumptions, and then based on those assumptions, we create this distribution. So that would be this bell curve up here. Then we take a sample. That should be number 2. Two number 1s in a row really don't make any sense, do they? So then we take a sample and we gather data. And this is where the stuff in the recording from last week, we're talking about taking a good sample, your sampling methods, getting a good enough sample size and all that would come into play. And we compare our results, we compare the data we got from that sample to that distribution. So now back up here to the curve. Let's say we get a result that's like way out here. So this is the value we got from our sample that we gathered. Well, that's way out on the edge of the curve. So the probability of being further out on the curve is just that area out there. If that probability is low enough, and usually 5% or 0.05 probability, if it's below that, then we say, hey, chances are our assumption was wrong. Because if our assumption was correct, it's very, very, very unlikely that we would get the results that we just did. So we're going to say our assumption is wrong. Because of that, if I want to compare our new drug here to drug A, which is the standard drug that's been used for years, and we take 2 groups, we put them in we select them, we compare their ages and all that stuff, so we get 2 very, very similar groups. And in the group that gets the new drug, we have a 71% recovery. In the group that got the old drug, we have a 66% recovery. Does that mean the new drug is better? Well, it's tough to say. Because on the curve, if they were the same, we would expect the results to line up. We assume, the assumption we're making is that the old drug is as good or better. And that's always the assumption we make, is that the status quo is the best. We don't want to make any changes unless we're absolutely sure. So we're going to make that claim that the new drug is as good or better. So we're looking at, this right here, the new being on the side of the new drug. Or the old drug, I should say. The old drug is as good or better. The new drug then, we do our sample, and the results coming in over here. In the sample, the new drug was slightly better. The question is that enough better to say that the assumption was incorrect? And the way I drew it here, the answer is no. It would have to be way over here. The new drug has to be a lot better before we make that assumption. Well, why? This was 5% better. Why is that not enough to say, hey, this new drug is better? It's enough to say the new drug shows promise, we're going to keep testing it. But there's a chance that we just happen to randomly select, even though we were careful about our age and all the other demographics. It's possible we just happened to randomly select people that we're going to get better anyway. And it's possible that we just happen to randomly select people for taking drug A, the old drug, that weren't going to recover no matter what. So that's called that sampling error, sampling bias. And I mentioned that a little bit in the recording, that sampling error, even though we do everything right to make as good of a sample as we can, we don't always get perfect samples. So that's the whole thing about statistics is if we could take perfect samples, most of the practices in statistics wouldn't be necessary because we could just compare the two numbers and say this one's higher. Most of what you would do in statistics involves figuring out, okay, how much different do they have to be before we can say that there's no way that was just random differences in the sample, that there really is a difference. Okay, so that's enough of that. Let's get back to the actual hands-on calculations. The reason I wanted to throw that out there is because that is the most misunderstood concept in statistics is what is it that you're really doing when you're testing and doing confidence intervals and all that stuff. That's all it is based on is you're making an assumption, you're sticking to that assumption, you're planning out that distribution, assuming that assumption is true, and then you are gathering data and putting it on there and seeing where it ends up. And if it's way out there compared to your assumption, then the assumption has got to be rejected. Right now, because of changes, you guys most likely are going to be going on to a 4-year degree at some point. A statistics course is something that is pretty surely in your future. So keep that in mind. By the way, we do offer a statistics course here for any of you that are looking for electives or whatever to fill up time if you're waiting to get into clinicals. Or if you finished clinicals and you're waiting to go on to finish off a 4-year degree, it's something to consider. So anyway, one of the things that was in the recording that I do want to go over with a little bit again is organizing data. We put in there are 2 types of data that we're going to look at. We have numerical, sometimes called quantitative, and we have categorical. Sometimes called qualitative. Bless you. What it deals with the question we are asking. The question we are asking is what determines what's called a random variable. And the answer to that question is what gives us our random variable. And so if the answer to that question is a number, then it is a numerical random variable. It's numerical data that we're gathering. In other words, the answer to that question is a quantity, quantitative. If the answer to that question puts us into a category, then it's a categorical variable that we're dealing with. It's measuring a quality of the person, not a quantity. So examples of numerical might be measuring height, age, blood pressure, cholesterol level, blood sugar, anything that's going to come up with a number. Categorical, favorite color, what disorder you have, or maybe even a broader category of what organ is defective, is a heart, lung, kidney, whatever condition that's being affected. Any question that has a yes or no answer is going to be categorical because it puts you as either in the group or not in the group. So we're going to start out with the categorical data here first, organizing categorical data. And I did mention this briefly in the recording. The simplest one I'm going to use is favorite color. And so let's say we're going to give people the choice between blue, red, and green. Those are the only three choices. And I'm going to start sampling people, and they're going to tell me their color. So I got a blue, a red, a green, a red, a blue, a red, a green, another red, a green, a blue, red, green, blue, red, blue, red, red. That's what I have. 8, 9, 10, 11, 12. And one more. Red. So let's say we've got a blue, green, blue, green, red, green, blue, green, red, blue, red, green, red. So I have 40 responses listed here. Looking at that, without counting, can anybody tell me which one's the most common? Red, somebody would say. Well, it's actually a quirk of the human brain that you can only take in between 7 and 13 things at once. So with 40 of them out here, there's no way you're really getting a good picture of the whole thing. So your brain actually looks at pieces of it. If you're looking right here, which one would your brain probably say is the most common? Blue. But if you're looking here, more likely to say red. Right in here, you would say green. So it's depending on where you focus here. So one of the ways that we can make this easier is to organize it into a table. And it is called a frequency table. And for categorical data like this, it's really simple. Here's just red, blue, and green. And it doesn't matter what order we put them in because there is no natural order to them. And over here, we're going to list the frequency. Now, I left a column in here because I'm going to do a tally here, just because that helps me to do this. So I'm just going to go through. I got blue, red, green, red, blue, red, green, red, green, blue, red, green, blue again, red, blue, red, red, blue, green, blue, blue, green, red. I have to move my line. Red, green, blue, green, green, red, blue, red, green, red. So now, come on. Now I can make my frequency. Now if I were actually making this frequency table, I would do the tally column and then I'd redo the frequency table without that in it because that really isn't part of the table. That's just helping me get the counts. So this is 17 red, 12 blue, and 11 green. You could have gathered that red was most common, but I would have never guessed that blue and green were that close. I would have just looked at it and thought blue was way more than green. So that is the frequency table. And this is where we would start a lot of those graphs we talked about in the last unit, the data graphs. Like a pie chart would be a perfect step to go next with this. Find the percent that each of them is out of 40 and construct that pie chart. So this is what, 42.5%, 30%, and 27.5%. So we can organize them, organize categorical data like that. Numerical data we can organize as well, but there are two types of numerical data we're going to look at. We're going to have what's called discrete and continuous. Discrete are things that can be counted. Like, how many classes are you taking right now? 1, 2, 3, 4, whatever. How many credits are you taking? 1, 2, 3, 4. How many cars do you own? 0, 1, 2, whatever. Those are things that can be counted. Those are discrete. Continuous is measured. Height is something that's measured. Weight is something that's measured. Continuous, things that are measured are never truly exact. There's always, it depends on the precision of what you're measuring it with. Continuous, one of the technical definitions of continuous is no matter how close two numbers are, you can always find a number in between them. Because no matter how close two people are in height, there's always a slight difference. They're never exactly the same. If you go down to a small enough unit of measurement, you can always find a difference between them. And that's what continuous is with that measured. So discrete is usually fairly simple. If I ask for a number of classes, being taken right now, and I'm not going to put out the raw data, I'm just going to throw it on the table here. If you're taking 0 classes, you're not a student, so you're not part of our group here. Well, let's say 1, 2, 3, or 4. Nobody in the sample we had more than 4 classes. So we might have 8, 19, 33, and 31. And there's our frequency distribution, frequency table of those classes. So you see that works out pretty much just like our categorical. Continuous is a little more difficult. Let's say I want to do height. Okay, well, let's say we have people that are, and I could go down to the 10th of an inch or whatever if I wanted to, or 100th or 1,000th of an inch. Well, let's just go down to the 10th for now. So we have 68.1, 69.3, 71.1, 67.9, 63.4, and so on. And we're going to you'll list out a bunch of heights here. The thing with continuous is you have to have quite a few measurements to make it worth making a table, because we're going to have to group them together. The reason it's grouped is, well, if you're measuring to the 10th or the 100th, there's no way you can list out each individual value and make it work. So we might have to make ranges. So the height, we might, instead of saying, 60 inches or whatever, we might say 60.1 to 64. 64.1 to 68. 68.1 to 72. 72.1 to 76. And then we'd list our frequencies. So we're not getting each individual value. Now it is possible to have that same effect with discrete numerical data if you just have such a wide range of single values. Like the reason I chose number of classes is because there's only going to be a few possibilities. But if I chose number of credits you're taking, you might be taking anywhere from 1 up to 19 or 20 credits right now. I wouldn't want to list all of them out separately. So I would probably group those as 0 to 4, 5 to 9, 10 to 14, 15 to 19, and group them that way. And this is always that first step, making these tables. That's the first step then to making those graphs we discussed at the end of the last unit. Well, one of the big keys in statistics is describing data numerically. We saw here organizing the data in tables, and we could take that next step as to what we saw in the last unit of then taking those tables and organizing them into graphs and charts. But a lot of times graphs and charts are clumsy, they take up a lot of space, and you can't get a lot of detail in them. We saw that if you're trying to get an exact number, I believe it was on the last page of this test, the top question, how many have this certain condition? Well, is that at 8 or 9 or at 10? And I accepted all three of those answers because you can't tell exactly. And that's one of the weaknesses we discussed about a graph, is getting exact values is tough to do. So if we want detailed exact information, we do have to describe it numerically. So looking at this bell curve again, let me try that again. That looks ugly. That's not a whole lot better, but let's try it. Let's go with it. Looking at this bell curve, there are a couple of things we can describe about it. Remember, we're looking at this number line being down below it here. We can describe the center of that bell curve. So for example, if I have another curve that looks like this, if I want to describe the difference between the green and the black curve, they have different centers. The center of the green curve is higher up the number line than the center of the black curve. If I want to describe the difference between the black and the red curve, they have the same center, but the red one is narrower. We would say that the black one is wider or more spread out. So the two things we're going to measure the most is center and spread. Spread is also sometimes referred to as dispersion. How far apart is the data dispersed? So I'm going to create a small set of data here for us to use. One, 2, 3, 4, 5, 6, 7, 8, 9. And let's put let's do 12 in there. So there's a set of 10 numbers that we're going to use. I'm just going to copy that so I can use it again when I need to. Our first measure of center that we're going to talk about is something called the mean. The mean is what we've all been doing since about 3rd or 4th grade. What we learned is the average. You add them together and divide by how many are there. So some symbols we're going to define here quick. N is the number that are in the set. So for this set, N equals what? 10. There's 10 numbers in the set. N equals 10. Another symbol looks like that. That's the sum, which means add them up. So the symbol for the mean, for the formula of the mean, looks like this. Sum of the x means add up all the values and divide by n, which is the number that's there. So if I add them all up, that'd be 14 plus 27 is 41. plus 18 is 57, plus 9 is 66, plus 15 is 81, plus 16 is 97, plus 21 is 118, plus 14 is 132, plus 16 is 148, plus 12 is 160, 160 over 10, did I add those up correctly? Somebody double check me. It's a Friday morning. Who knows where my mind is? 162? That's very possible. 162. I'm slipping. So that'd be 16.2 I'm getting for my mean. 162 divided by 10. So that one we're pretty comfortable with. We've been seeing that one for a few years. The next one is the median. The median is often referred to as the middle. To do the median, generally we first have to put them in order. So I'm going to put my set back down here. So the first thing I'm going to do is put them in order. Always my first step. What's my smallest number here? 9. That looks like 12. 14. Another 14. 15. 16 and 16. 18. 21, 27, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, good, we got them all. Second step. Always smallest to largest, yes. Find the position of the median. The position of the median, there's two possibilities. If n is even, we take 0.5 or 1/2 times n, and we'll get a number. So for this case, it is 0.5 times 10. We get a number which is 5. If n is even, of course, this will be a whole number. The median is between that position and the next one. So that's a 5, so it's between the 5th and 6th position. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are positions. It's between the 5th and 6th. So it's between 15 and 16. So now we're just going to average those together. 15 plus 16 divided by 2 is 15.5 is the median. Now I'm going to add a number on the end here. I'm just going to put a 29 out here. The only reason I'm doing that is because this was if n is even. The next case is if n is odd. We're going to start out doing the same thing. So we got 11 numbers up there now. So 0.5 times 11 is 5.5. If n is odd, this is going to be a decimal. If you get a decimal, you round up. Now, if we're talking about percentiles and stuff like that we're going to talk about later. You always round up. Even if it's 5.1, you always round up. So our median is in the 6th position. So up here, this is now numbered to 11. The 6th position is just the 16. So the mean of that original set was 16.2. The median was the 15.5. This 16 is just what the extra number put in there. The next one is the mode. The mode is the number that occurs the most often. There is no formula for the mode. All you got to do is look in the data and see which one occurs most often. If you have them listed from smallest to largest like I do now, it's not so hard to find. If they're listed randomly like this, that can be really trouble. So you're going to have to sort them pretty much to find it. But we see here that we have the 14 appears twice and the 16 appears twice. Depending on what textbook you're looking at, some textbooks say you have one mode or there isn't one. Some say you can have up to 2. Other textbooks go into this long explanation of the sample size. You can have up to the square root of n minus 1 modes. We're not going to get into that. For our purposes here, there's either one mode or there isn't one. So here, because there's 2 numbers that both appear twice, this one has no mode. There has to be clearly one number that is the most often. And usually that's the case in small data sets like this. There really isn't a mode. You have to have larger data sets for there really to be a mode that shows up. So now the question with these measures of center, which measure of center is best? How many of you, show of hands, would say the mean is the best measure of center? How many of you would say the median? A few of you. How many would say the mode? How many would say you really don't care? Most of you. Okay. Well, the mode is an easy one to find, but it's not a very good measure of center, especially in smaller data sets. So it usually does come down to the mean and the median. A lot of people like the mean because you've got a formula. You add them up and you divide. And it's something you've been doing since you were young, so you're familiar with it. But let me show you an example here of just a few numbers. We're going to go 14, 20, 27, 31. There's a data set. Let's find the mean and the median. The mean, if I add those all up, what do we got? 20, 34, 61, 92 divided by 4. 23, does that look right? The median, well, 1, 2, 3, 4. 0.5 times 4 is 2, so it's between the second and third. Also, in a small data set like this, by the way, you can see where the middle is. I mean, I could have up here with a small data set, I could have, for them to find the median, I could have just started crossing off the ends. And see, oh, I end up with 2 numbers in the middle. For bigger data sets, it's not as easy. But anyway, it's between 20 and 27. So 20 plus 27 divided by 2 is 23.5. Relatively close to the same. And in a good data set, in a really good data set, the mean and the median will be the same number. But in a good data set, they will be really, really close to the same. Now we're going to look at a data set that looks like this. Same numbers, I just added one to it. Now for the mean. If I add those all up, what's that? 157 divided by 5. So we get 31.2. What's that? 0.4. Thank you. 31.4 is our mean. Our median, well, there's 5 numbers. So 0.5 times 5 is going to be 2.5, which is telling me that the median is the number in which position? Round up to the 3rd position. So it's 27. Which one was affected the most here? Well, the mean went from 23 all the way up to 31. The median went from 23 up to 27. The mean was affected the most. So the median is generally viewed as a better measure of center because it's more stable. I'll show you an example. In 1983, University of Virginia. Got a capital U, just not to be insulting. Published that the average, and that's the term they used, was average starting salary for a 4-year bachelor's degree in marketing. That year was just over $78,000. Now, if you go back right now, $78,000 would be a really good salary coming out of a 4-year degree. You go back to 1983, your average high school teacher was making about $16,000 a year starting out. $78,000 was a phenomenal amount of money. What they neglected to disclose was that one of those graduates was a man by the name of Ralph Sampson. Ralph Sampson was 7'4", played on the University of Virginia basketball team, and was a 2-time NCAA basketball player of the year. Was the first draft choice in the NBA draft by the Houston Rockets. And you can probably guess he made a few million that year or more. It takes a lot of $20,000 marketing graduates to average out a multi-million-dollar contract to $78,000. In fact, Mr. Sampson was the only one in the group to make more than $33,000 that year. The median, so this was obviously a mean. The median of that group was between 21 and 22,000. Which still isn't bad, but it's not 78,000. So you can see the mean, it's highly affected by those, what they call outliers, those really radical really high numbers or really low numbers on the other side of it. Okay, it's time for our break, so let's go ahead and take our break. We'll come back at 11:30 and we'll start talking about measures of spread.